any questions from last time? I know Jeremy has one. Jeremy has one. Jeremy, right?
Maybe.
Yeah, okay. Well, the email you sent me. So let me just mention that. So the calculation we did yesterday was motivated by LSZ formula and the expansion that we can do for the endpoint function in the interacting vacuum in terms of the free Dyson series in the free vacuum. So this is something that Dan treated in the context of scalar field theory, and I'm not going to. Well, I wasn't going to go into detail, and I won't. But it's worth just mentioning this, right? Just for conceptual clarity. So the setup yesterday was that we applied the LSZ formula, and what it does is that it extracts from this general object. So for us, it would be psi 1, psi 2, psi 3 bar, psi 4 bar. Say for 4 fermion and an anti-fermion scattering. It basically extracts this part where there are particles coming in and particles going out, and there's some kind of interaction between them. And it assumes, see that in the LSZ formulation, you apply the wave operator, and you apply an exponential of plus I p dot x or minus e to the power minus I p dot x to extract whether you're looking at the incoming or outgoing particles. So what that means is that you are basically cutting off the exact external propagators because the wave operator has singularity at those exact propagators, and you are given with the stuff that happens in between. So this by itself is a non-perturbative result. This has nothing to do with perturbation theory. And if we could compute this thing without using perturbation theory, we'd have exact results to all orders, and that would be wonderful, but that's not how life is. So one has to actually resort to perturbation theory to compute these things. And in perturbation theory, Dan told you that this object can then also be expanded. So there is some technicality about sending the time to 1 minus plus, putting a small negative imaginary part in the positive time. And then we can project this to an interaction picture formula which involves the Dyson series. Here is our interaction Hamiltonian in the interaction picture. And then we have the original. So now everything is an interaction picture. And so the mode operators are the free operators. And not only that, we are actually, this formula, which I derived in the quantum mechanical context in the front-end quantum mechanics lecture that I gave, but it's extremely relevant here, where you have the time-ordered exponential of blah, blah, blah without these guys. So let me remind you, what this denominator does is that it gets rid of all the vacuum diagrams. However, the numerator will still have disconnected components, right? But those disconnected components are killed by the LSZ formula because those disconnected components would correspond to stuff like that, where the incoming and the outgoing particle didn't really interact with the other particles. So that's how the LSZ formula and this, the Dyson series expansion of the exact 4-point function in terms of evaluated in the exact vacuum in terms of this object expressed in interaction picture field operators and the free vacuum allows us to set up the perturbation theory framework that we did today. So notice the result. The result is that when we do the expansion, we expanded this guy yesterday, right? Yesterday we expanded in the first order. First we expanded there's a 1, and that's just the transfer matrix, the identity matrix, nothing is happening. We ignored that. The first order term for the nucleon to 2 nucleon to 2 nucleon scattering was 0. So we just did the second order term of this expansion, okay? And we only kept the connected parts of it, and that's because, of the LSZ, it has already gotten rid of the disconnected part, okay? So this is a little bit of a subtle and complicated story, and I'm not sure I understand all the subtleties of it, but I think that's the rough outline of the story. But this is the conceptual framework in which we do perturbation theory calculations. So yesterday, we were discussing classical aspect of the gauge potential in electromagnetism, and I was arguing that classical aspect is analogous to what happens in general relativity. Okay, so let's pick up there and. So I ended with some kind of a chart where I said, well, GR has some Christoffel symbol, which I'm going to call a potential. Remember, in physics, potentials are not things that we really observe. They're, experiments observe kind of forces or field strengths or curvature. So GR has a potential, which is called the Christoffel symbol. And from this potential, you can derive curvature or field strength. And those are the Riemann tensors. That is the Riemann tensor. And the Riemann tensor is given by something like the commutator of 2 covariant derivatives acting on some vector, right? This is the famous Ricci identity. And in E&M, there is an analogy. And the analogy is its potential is given by a 4-vector potential, and its curvature is given by some f mu nu. And suppose that f mu nu was acting on some wave function, then its action on the wave function is given by a different covariant derivative acting on this, where this guy, I don't have to tell you what the covariant derivative in GR is. You already know this. But let's just, for completeness, do this. It's something like, is this a minus or plus? I think it's a minus, right? So that's the definition of the covariant derivative in GR. And in electromagnetism, interacting, say, with some Dirac wave function has this form. This is some coupling constant, strength of interaction. And we shall see that there is some kind of a gauge group associated with these guys. And, okay. And for E&M, it's U1. And for GR, it is, I think, GL, general linear group in 4 dimensions with real matrices. And you will see in the next QFT2 lecture, there's a generalization of electromagnetism called Yang-Mills theory. And in that, you will have a gauge potential, but now it's matrix valued. So it's a Lie algebra valued object. And there will be these analogous objects here. And here you can have UN or SUN or ON, SON, any group that is compact. Okay? So there are, in Yang-Mills theory, you will have an analogous object here. And here you will have something like this, where now this thing is like Lie algebra valued matrix. Okay, so there's a very consistent mathematical theme going through all of physics. Okay, that was like a diversion. Let us come back to discussing electromagnetism. So we can express the first of Maxwell's equations in relativistic form in terms of A mu, and it takes this form, box minus of A mu acting on the divergence of A. And if you put a current here, okay, where box means this. This is the covariant wave operator. More explicitly, it's this object. And there is a C equals to 1 set here because the wave operator usually has the like the speed of the wave somewhere inside there, and this thing is for divergence of A. Okay, and in terms of A mu, the second Maxwell's equation, which was this thing, it becomes just an identity because partial derivatives commute and we are antisymmetrizing in all the indices. So this is automatic, this is an identity in these variables. So in quantum mechanics, right. So then I talked about one of the needs that we understand for A mu. I motivated that by saying, say, the Bohm-Aharonov knock effect. There's a lot of non-trivial examples in quantum mechanics and quantum field theory to motivate why A mu is a natural choice. It's not like, you have to use A mu, but, there are some, it's like, I don't know, some people will argue that you can do quantum mechanics without complex numbers just by using probabilities and stuff like that. In my opinion, it's a little, what's the word I'm looking for? Masochistic. But I'm open. If somebody shows me an elegant way of doing quantum mechanics without using complex numbers and wave functions in the Hilbert spaces, I'll jump and change the band and jump to that bandwagon. But I haven't seen such an elegant formulation. Anyway, sorry, I didn't want to go there, but anyway, it happened. So we only have to worry about this equation when we are talking about Lagrangian. So let's take the free equation. And then it turns out that, well, it's not very hard to see that you can derive this equation from this Lagrangian density. So I would like you to take, so some of you have done this. For some of you, this is old hat. You've done this. But I would like you to now derive this equation from this equation, for those of you who haven't done this before, because it gives you a good opportunity to work with indices. Okay? And I would recommend, if you have seen this before, be a nice citizen and help someone or discuss with someone who hasn't done this before and has questions, okay? This is like, let's take a few minutes and do this, okay? Unless you've done this already. But I know that some of you haven't done all of indices, so the hint is that write this out like this. And perhaps consider what this is. Just work this out. That's all you need to know. You don't have to even finish the exercise. Just work this out. Okay. Have you guys figured this out? All right. What does this term give you? Can anyone tell me?
0.
0. Why?
Because there are no like free A's in
Right.
Lagrangian.
So in the Lagrangians, the A's always come with derivatives because they're in A. So this term doesn't give you anything. And if I compute now this term, this object, partial derivatives are wonderful things. From the first guy, we are going to get a delta function which says that if the index of this delta is not equal to the index of this delta, it has to be 0. So there should be a delta function saying this. And for this, the index of this thing has to be equal to the index of this thing. So there has to be something of, well, it has to be there. And because these indices are downstairs, but it's in the denominator, they have to be upstairs in the numerator. And from the second term, we get sigma has to be equal to nu. And this thing, mu, has to be equal to rho. So, and here you see, you have to use a Leibniz property. So you can actually lower these indices. So when you apply this thing on this Lagrangian, you get 2 times f, and then the derivative acts on one of the f's and gives you this thing. So you have to then contract that. So this gives you, there's this thing outside, and inside you get delta mu delta nu minus delta nu delta mu sigma rho, and you get up to some number, you get f mu nu. Right? Right. And so then what you do is that, okay, this is equals to 0. And this mu, this delta sets this to rho and this to sigma. The other guy sets them in the opposite order. But then sigma and rho, but this is antisymmetrized, so those two things actually add up to give you rho sigma. Okay, so it's an easy exercise, but it's actually not easy if you haven't done this before, and you have to do this. Okay, so right. Now, before we move on to the quantum mechanics of it, quantum field theory of it all, let's make a few comments about the classical equations. Hello? Okay, it's stuck. All right. See that because F mu nu is antisymmetric, that means that, so a term like this, there is no time derivative of A0 in the Lagrangian. Okay? So A0 is a Lagrange multiplier. So you can integrate that out. Well, if you look at the equations of motion for A0 then, it gives you this equation, and if you use the definition of what E is, then you get Gauss's law. It turns out that Gauss's law is a constraint. So it is a constraint equation. From this point of view. The other thing, although I mentioned this before, but this needs to be repeated. If I make a transformation of my gauge field, of my vector potential field, so I replace A mu of x by another A mu of A prime, where it's related to the original A mu by a gradient of some scalar function, chi is some scalar function, and this is a four-dimensional gradient, then see that F mu nu doesn't change. So this symmetry is called a gauge symmetry. It is not a symmetry it's not a global symmetry, so it's not a global symmetry. So you can't use Noether's theorem here, and there is no constant of motion associated with the symmetry. It's actually a redundancy of description. A mu and A mu prime, they describe the same physics. And in some cases, such as the, I think the Dirac's treatment of the magnetic monopole, you actually need two different A mu's to describe a physical system. But let's not go there. What do I mean by redundancy of description? You might say, I've never seen this before. But I'm going to say you have. And you have seen it in GR. In GR, our theory is invariant under general coordinate transformation. So you say that if this were my coordinates, I can define new coordinates, x prime of mu, which are some general functions of the original x's. They just have to be, they're just general functions, right? And then your vectors transform like some something like this, right? The Jacobian matrix times those vectors, right? And you know that the curvature tensor also transforms like this, right? Here it's because the group is U1, the curvature tensor doesn't transform, but you know that's just a. But you'll see in Yang-Mills, F mu nu in Yang-Mills will actually transform with U F mu nu U inverse, like the way that this is going to be analogous to the way that Riemann tensor transforms in GR. So yeah, you have seen this redundancy of description before in GR. So it turns out to do physics, you need to get rid of this redundancy of description, especially if you're going to have sensible quantum physics. And you might say, why? I will give you an example of why today. And you will see other examples in QFT2. And there are deeper reasons, which I will not go into, but we can talk about that later. So, gate choices. So using the fact that my equations are invariant under this transformation, you can show that you can set this condition and then all you're left with are the physical degrees of freedom. So for an electromagnetic field, you expect two polarizations of your field, but this guy has 4 components, and by using this condition, you get rid of 2 of the components of A mu. And this choice is known as the Coulomb gauge. So the choices of these conditions are known as gauge choices. And the Coulomb gauge is not covariant. But it's physical. But what I mean is that from 4 degrees of freedom of A mu, you are reduced to 2 degrees of freedom. For relativistic quantum field theory, also for doing scattering amplitude at high energies which are necessarily relativistic, this is not a convenient choice. A more convenient choice is a covariant choice known as Lorentz gauge. And as some of you may know, the Lorentz gauge is Lorentz invariant. And the Lorentz gauge is choosing this to be 0. So this is covariant or Lorentz invariant. These 2 Lorentzes are not the same. As was pointed out by Jackson. So the Lorentz gauge is Lorentz invariant. There's a more generalization of this Lorentz invariant gauge. Some people work with, if you have, instead of 0, you have some, say, function, I don't know, like alpha, some scalar function here. This is sometimes called the Feynman gauge. So in today's lecture and for the rest of the course, we are going to use the Lorentz gauge. So in some sense, we are going to impose this condition. But we are going to see, we are going to run into some problems imposing this condition as an operator equation. So if I use the Lorentz gauge condition, my equations of motion become very simple. So these are solved. The solutions are plane wave solutions. So there are some coefficient vectors which can depend on k. And these vectors are called polarization vectors. Then our gauge condition says, so our gauge condition says that if I plug this into this guy, that the polarization vectors and the momentum vector, or momentum vector, have to be orthogonal. And our equation of motion says that k has to be null. So in principle, you have 4 independent polarization vectors, but the gauge condition eliminates 1. In the Lorentz gauge, we can still make another gauge transformation. We can make another gauge transformation, and as long as alpha, this gauge function, satisfies this equation, it does not change the Lorentz gauge. We are not going out, we are not going to another gauge. See? If you replace this, the A here by this, as long as A satisfies this gauge condition remains unchanged. So this means that, if you were to solve this equation, it'll have some form like this. So this is called a residual gauge symmetry. This is a residual gauge symmetry. Under this residual gauge symmetry, what happens is that our polarization tensor, a vector, changes up to a 4 momentum vector, as we see from here. So you can use this to set one of the polarizations to 0. So use this freedom to set, I'll get rid of that. This doesn't move, right? All right. In that case, I guess we are just stuck with one board here, which I will use for now. This is the problem with technology. It breaks down. So we can use the residual gauge symmetry and set, say, one of the polarization vectors to 0. Then our gauge condition is, sorry, there was a typo in the notes. So our gauge condition then in momentum space is this thing, so that equation. So epsilon has 3 components left, but this equation eliminates one of them. So that's how we see that epsilon has 2 degrees of freedom. It's a little subtle and confusing, if you ask me, but so what are the interpretation of the gauge conditions? There's a nice picture. Suppose you have some space. Let's call it big G. And it's a space of all solutions. Big G is the space of all A mu, which are equations of, which solve Maxwell's equations. In that space, we have what are known as gauge orbits. So suppose you have one physical solution here. That's physical solution number 1. Suppose you have a different physical solution. Number 2. Now, if you make a gauge transformation, what happens is that you move from this physical solution to another equivalent physical solution along these gauge orbits. So these are called the gauge orbits. So all these yellow lines, every point on a given yellow line is physically equivalent. And they are related by a gauge transformation. Making a gauge choice is saying that you are choosing to slice through this space and picking out a representative solution from each equivalence class of solutions. Okay, so this is a gauge choice number 1, say the Lorentz gauge. And say this is the psi gauge. And So this is the Tibra gauge, which is not a very good gauge because you see there's overcounting. So that's an example of a bad gauge choice. And these copies are known as Gribov copies. Anyway, I once named one of the Psi photocopier Gribov. No one got the joke. Anyway. So that's the geometric meaning of gauge fixing. So let's quantize our theory in the Lorentz gauge. So we want to quantize the theory, but in the Lorentz gauge. Now, it turns out that the Lorentz gauge condition is problematic as an operator equation. And we'll see that. Before we get to that, the equation, let's start with the equation of motion before we get to the Lagrangian. The equation of motion is this, and we know that it has plane wave solutions. That's very easy to see. So a general solution would be given by our friend now. We have 4 polarizations, so you have to sum over the polarization. They go from 1 to 4. And let me just label them as 0 to 3. And these polarizations have a vector index, but they also have a label, lambda. And they are functions of P. And then we have Fourier coefficients, which upon quantization will become an annihilation operator. And because A is a real field, we have to have a complex conjugation here. So this just comes from the fact that we have solved this for plane wave, and this is the more general solution. So these guys, they transform as a vector, as a 4 vector, and there are 4 of these. So this condition eliminates one polarization. So we know from classical electromagnetism that the physical polarization will have this form. It's a okay, I'll come to that. That there is no time-like polarization. So this is some 3 vector. And if the momentum of the particle is 3, momentum of the photon is p, then they have to be transverse to that. Electromagnetic waves are transverse waves. But we also have a 4th polarization, which is proportional to this. because the momentum, because the momentum of electromagnetic wave is, that comes from our equation of motion. Therefore, a polarization which is light-like, so this is light-like, this solves this equation. So that's another, so these are the, so there's a solution like that. So the 3 solutions are these things. So this is the weird guy who is somehow not physical.
Is that lambda 3?
It's on mu.
Oh yeah, thank you. So let's make some normalization choices for mathematical convenience. So I want to emphasize this is just a normalization choice which is consistent to make rather than something deeply physical. So let's normalize our vectors, our polarization. So first let's completeness. For covariance, it turns out, and you can check this by putting in, several different kinds of values, that you might have said, why didn't I put delta function here? Because these are just labels. It turns out that if you put delta function here, then you actually don't get a covariant, that it actually will, this expression will not be covariant. Because, these guys are vectors, this is our metric tensor, right? And the orthonormality so the spatial components have negative norms. So for convenience, we are going to choose a particular reference frame. So choose a reference frame. And let's just assume that K mu is a vector, null vector along the z direction. And let's choose the 0th component of epsilon to be this. It has to be consistent with these equations. Then the 3rd component is longitudinal, and the physical components is transverse to these. So the physical component can be, say, how should I say, E1. So this is E1, and this is 0, this is 1, E1, this is 2, and this is E2, this is 2, this is E2 of 2. And so this is, let's make these choices. So before we quantize, observe that this equation cannot be derived from the Maxwell-Lagrangian, because this is the gauge fixed equation. So we actually need to use a different Lagrangian to quantize the theory, which is, so let's call this electromagnetism. We add a term which explicitly breaks the gauge asymmetry, and this Lagrangian is called gauge fixing, and we are going to choose this in such a way that we get this as our equation of motion, and it has this form. So if you add these two guys together and up to some total derivative terms, you get this. And you might say, why are we fixing the gauge? You know, what is, I'm all confused. There's a very simple reason. You will see in QFT2, from the point of view of the Lagrangian, say you have some action with some Lagrangian in it, and you should be able to express your action in terms of your basic fields, some operator, wave operator, acting on your basic fields like this. Okay? This wave operator is the inverse of the Green's function, or the propagator. Let's call it propagator. Let's call it, for electromagnetism, the Feynman propagator. And it'll give you something delta, right? So this, suppose this has x here, so this is some delta for x minus y. However, this doesn't work. If you have a gauge theory, you can show that this operator has functions which are zero modes of that operator. So in matrix language, what we are saying is that you have some matrix, and it has a vector, a non-zero vector that the matrix annihilates, which means that the determinant of that matrix is 0. That is, it has 0 eigenvalues. Therefore, it is not invertible. The wave operator is a matrix of sorts. And the Feynman propagator is the inverse of your wave operator. Okay? Therefore, if this problem was not fixed, this equation doesn't have a, doesn't exist. It turns out this is related to the fact that your Lagrangian has a gauge symmetry. And that is a reason, before we can do any physics, we have to gauge fix it. And that's why we add the gauge fixing term. So the theory that we're quantizing is not really electromagnetism. It's something plus. Electromagnetism plus something. But I think Francois tells you at some point that how you can actually take an average over all this gauge fixing term, and you can show that the physics is actually not dependent on your particular choice of the gauge fixing term. That's beyond my discourse. But Francois will make a comment on it, and I will make a note to remind him to make a comment on it. If I forget, please ask him. All right. Okay. So by the way, the tutorial today, we are going to do a lot of minus signs for Feynman rules for fermions. So please show up. So what is so A mu? What is the conjugate of that? The conjugate is, using the Lagrangian above, is this object. So this is the canonically conjugate momentum. So because of the spin statistics theorem, we impose commutation relationships, and the commutation relationship between the field, so equal time commutation relationship. So these guys can be different at the time, but the time is the same. And for pi, there's a dot. What is this minus sign for? We chose this minus sign so that the spatial components of this guy has a positive sign. And we'll see that that's very important, because you'll see that corresponding to the fact that the physical polarization vectors are the epsilon 1 and 2, will correspond to the fact that, you know, there will be creation operators which come from, say, A1 and A2, which are the physical creation operators. So for those guys, we better have a plus sign around here. Otherwise, our inner product of states that we'll create with them will be negative. So you're saying, what do you mean? That the zeroth component of these operators will create states which have negative norm? Yes. And that is the price that you pay for doing a covariant quantization. And we will show how you can actually get rid of those negative norm states in a clever way. So the Feynman propagator here is very easy to define. See, the equation of motion, which is this, guys, it's nothing but like 4 Klein-Gordon equations, right, with 0 mass. So the Feynman propagator here is, it's a gauge-dependent object, so it's a gauge-dependent object. As I said, if you didn't choose a gauge, this thing wouldn't exist. It's a time ordering of a mu of x, a nu of y, and basically it's the 0 mass limit of the Feynman propagator for a scalar, real scalar field, multiplied by a metric tensor. Explicitly, that's what this is. So these guys then lead to the commutation relationship. I wrote anti-commutation in my lecture notes. I'm sorry about that. To the following commutation relationship, and let's go there. I'm going much more slowly than I anticipated, but that's all right. Usually the last lecture is extra short, so that means that tomorrow's lecture will actually fill out the whole hour and a half. So the commutation relationship we get So, I mean, these are, I think I put them upstairs before, but now I'm putting them downstairs. And the others are 0. As I mentioned earlier, if you have a state created by A0 of k, dagger of k, that state has negative norm. And that's because, yeah. Right? What am I missing here? Dagger. So what do we do with this? First, notice that the Lorentz gauge condition doesn't make sense as an operator equation. And why is that? If you compute this, so for not just equal time, for any arbitrary time, that actually gives you the Feynman propagator. Now, if you take the derivative with respect to x, if this were true, then the left-hand side would be 0. But from the expression of the Feynman propagator, we see the right-hand side is not 0. And therefore, this is not, the Lorentz gauge condition is not a consistent condition to impose on this theory as it is. However, there's a weaker condition that we can impose. And that condition, turns out, also kills off states which have negative norms. And that condition is called the Gupta-Bloiler condition. So instead of this, we say we take the positive frequency part of A mu. Recall that the positive frequency of A mu contains the annihilation operators, and we can take its derivative, and we say that a physical state must be annihilated by this. So this condition is the Gupta-Bloiler condition. If you take the Hermitian conjugate of this equation, you get this thing, right? Because the A plus is the Hermitian conjugate of A minus. And then we can put these two together. Then we get A mu plus, sorry, there's a mu upstairs, A mu minus in other words, physical states, if you sandwich this thing between physical states, you get 0. So in some sense, the Lorentz gauge condition is valid, but as an expectation value. Okay, so this is a much weaker condition, right? It's a condition not on the operators, it's a condition on the Hilbert space. So what does this do for us? Remember, let's choose these 4 vectors. And then if you now look at this condition in Fourier space, so if you look at them, what they mean in terms of the modes, you can see in that reference frame that the longitudinal part and which is unphysical. You know that electromagnetic waves are not longitudinal waves. And also the light-like part, which is the negative norm part, they act on physical states like that. And this means that you can actually use this to eliminate negative norm states and longitudinal states from your physical theories. So let's so if we compute the Hamiltonian, which will be normal ordered, then this is what you get. It's just a sum of all the number operators in all the polarizations. So on the face of it, you seem to be computing. We seem to be taking into account both the polarization, the null and the longitudinal polarization states. But if you now say, okay, I'm going to take the expectation value of this normal order Hamiltonian between some physical state, then if you look at the contribution from lambda 0 and lambda 3, you will get this, right? A0 dagger k, A0 of k, minus, because of this guy, A3 dagger of k, A3 dagger of k. Right? And then you can say, okay, what we can do is we can rewrite this we can subtract from it a cross term and add, of course, the same thing. Then this is a but the Gupta-Broiler condition says that this is 0. And its Hermitian conjugate says that this is 0. So this is 0. So we see that the negative norm state and the longitudinal state, they don't contribute to the energy. And you can show this, that they actually don't contribute from physical processes. Okay, so the covariant quantization involves working with a much larger space than both the longitudinal, which has both these unphysical states. And this is a price you pay for covariance. You will see again and again and again, if you do quantization of any kind of gauge theory, there's always a conflict between a covariant formulation of the covariant quantization of the theory. You always have to pay a price, and the price is there will always be some kind of unphysical degrees of freedom which you will have to manage to. You'll have to show that they go away. This happens again and again. Okay, and so I have 3 more minutes, but I don't think I'm going to start with the next topic in those 3 minutes. So, but do you have any questions? I sent you the lecture notes yesterday for what I hoped I would get to today, but I didn't. I will get to that tomorrow. Okay. And I've already posted the questions that I'm going to ask in the interview, but since I'm giving out handwritten lecture notes, I will make some questions for these lectures, and I'll email them to you sometime today, okay? So that they'll help you study. Any questions about all this? Yeah?
The 2 last lines on the left.
Yeah?
How come you're able to say that they're equal?
Oh, I subtracted something and then I added the same thing. Okay. Anything else?
By this lambda index in general, like why are we, when we write down the solution of A mu, why are we summing over lambda? What is lambda?
Okay, so yeah, when we first solved this equation, we said this is a 4 vector, right? So it should have, we took our ansatz to be this. Okay, so this is a 4 vector. Okay, so it has 4 independent components, and so we made some choices, but we labeled these 4 independent choices with some label lambda, and I didn't go into it, but the consistent way of normalizing these things is actually, the consistent way of normalizing these things is actually to use a covariant normalization. Otherwise, you can kind of check that your equations and your relationships are no longer covariant. If, say, if you were trying to put a delta here, for example, it would not work out. And we also chose the completeness relationship that they satisfy are also so because of these 4 independent ones, because this is a linear equation, you can write this as summed over all the momentum and summed over all the polarization. And then the A's are the Fourier coefficients. So this is a lambda. And then these are functions of P. And you also need Fourier coefficients. And there will be for each lambda, there will be a different Fourier coefficient, each epsilon. And plus complex conjugate, because this thing is real, okay? The tutorial is at 2 today, okay? If you have any more questions, come and ask me.